Hello, and welcome to the Grundfos SmartFlow SQE training program. This program has been created for you in response to the huge success of the SQE product line and the constant desire of distributors and dealers to improve their knowledge of this innovative constant pressure product. The program is made up of individual standalone modules which can be viewed in any order and include a SmartFlow introduction, a system components module, and the diagnostics module.
The textbook for this course is the CU 301 Installation and Operating Manual, referred to as the INO. This booklet is included in every CU 301 carton or can be downloaded from our website at www.grundfos.com.
Please take the time to refer to this book as instructed during the training, and you will find it will greatly increase your knowledge and discover it to be a valuable resource for answering almost all of your questions. The students that have taken the 30 minutes or so required to read the entire INO have a great advantage over those that have not. We strongly encourage you to read the entire book.
The objective of this module is to help you gain an in-depth understanding of the components and the operational fundamentals of each of those components in the SmartFlow system. First, a brief overview of the individual components used in the system, then we'll discuss each in greater detail. Let's start with the SQE. That's the actual pump and the motor. Models range from half horsepower up through 1.5 horsepower, with flow rates up to 30 gallons per minute. All models are single-phase 2-wire, powered by either 115 or 230 volts. The SQE's narrow 3-inch diameter eases installation in crooked or tight wells, and its extreme lightweight makes it easy to handle. The largest model weighs only 16 pounds. The SQE utilizes an integrated variable frequency drive. That is, the VFD is built into the motor. Next, the control unit. The CU 301 serves as the human interface, allowing the user to operate and view the status of the pump. It also serves as a control and communication interface to the SQE, designed to read the pressure sensor and then control operation of the pump to maintain constant pressure. The pressure sensor is the feedback element, which measures the actual water pressure and sends that information back to the CU 301. And finally, the fourth component of the system, the pressure tank. Only a small 2-gallon tank is required and has the advantage of taking up a small amount of space and is less costly than the larger tanks used in conventional systems. As shown in this photo, the system can be installed in a very compact space. Let's begin discussing the individual components now in even greater detail, starting with the SQE pump and motor. There's a lot of information contained in the model designation. In this example, the first 2 digits refer to the pump's rated flow, 10 gallons per minute. The 3 letters SQE indicate that the motor is of the SQ family, with the E indicating the unit is electronically controlled. The next 2 digits, 05, define the motor as 1/2 horsepower, and the last 3 digits indicate the maximum head the pump will produce at its rated flow. In this example, the unit will produce 10 gallons per minute at 160 feet of head. As mentioned earlier, the SQE contains a variable frequency drive, or a VFD for short. Grundfos has taken a very innovative approach with the design of the SQE by placing the variable frequency drive in the motor itself. This had never been done before and has not been duplicated by anyone since. By controlling the frequency of the voltage applied to the motor, the speed can thus be changed, resulting in constant pressure, synchronized with the demand. There are a number of advantages and benefits to placing the VFD in the motor. One is that it minimizes the number of conductors in the drop cable. The SQE utilizes single-phase 2-wire drop cable. A more important point is heat dissipation. By their very nature, all VFDs generate heat. If you've ever looked at traditional VFDs, you'll note that they have one thing in common: fans and large cooling fins. Since the SQE is submerged in cool water, it helps keep the heat down and allows the use of smaller, more efficient components which operate at lower temperatures, ensuring a long life. Lastly, placing intelligence in the motor allows for new possibilities out of reach for conventional systems. By definition, the SQE electronics are a computer, and by incorporating sensors into the motor and assigning the computer to measure performance and conduct diagnostics, new levels of reliability and long life can be achieved. Details of these capabilities will be discussed at greater length as we progress. Many of you are familiar with conventional pump curves, with their one curve reflecting their single-speed operation. But SQEs have essentially infinite curves located between its maximum and minimum speeds. This picture shows a typical SQE performance curve. Note the broad operating range achieved when changing the pump's operational speed. The upper curve represents the performance at the system's maximum speed, and the lower curve its minimum performance. The colored area between the curves represents the range of operation the pump is capable of as its speed is altered. All SQEs come standard with the built-in soft start feature. What's so great about that? Well, when a conventional pressure switch starts the motor, it instantaneously applies full voltage and current, causing an inrush current flow of approximately 5 times its nameplate rating. Passing 5 times normal current through the motor causes a temporary overheating of the windings, which must be allowed to cool before attempting another startup. That's why motor specifications often include a maximum number of starts per hour or per day. It's to give the motor windings time to cool from the effects of starting. The soft start feature built into the SQE eliminates this effect by gradually applying current to the motor over the course of 2 seconds, as illustrated by this chart. On the chart, the vertical axis represents amps, and the horizontal axis represents time. The chart shows 2 amp curves. The one on the top illustrates the inrush amp flow into a pressure switch started motor, and the lower curve the gradual amp flow into the SQE soft start motor. As you can see, there's no inrush current applied to the SQE motor windings. The end result is that starting the motor does not overheat the windings, and therefore there are no limitations on the number of starts per hour or day with the SQE system. Another advantage of soft starting the motor is the significant reduction of starting torque. The larger the motor, the greater the torque. It's a force that must be compensated for in conventional systems by the use of torque arresters or other means in order to minimize mechanical stresses on piping systems. While it was noted earlier that the SQE power input is single phase, the SQE motor is actually a 3-phase. The built-in VFD converts the single phase to 3-phase, and therefore the system has a higher starting torque associated with 3-phase motors. Due to the built-in electronics in the SQ and the SQE, a number of advanced protection features are now incorporated into the unit as standard equipment. Whereas in conventional systems, these important protection features must be added as costly, optional accessories. Let's review the list. Dry run protection. Remember, submersible pumps are water lubricated, and if you pump the well dry, you remove the lubrication, and it won't take long to damage the pump end if it's spinning dry. So it's important to protect pumps from running dry. The SQE detects dry run when the watts consumed falls below a factory set dry run threshold for a period of 5 seconds, and the motor speed is within 1,000 RPMs of the maximum speed. If detected, the motor will shut down, and the fault is automatically reset after a 5-minute delay. Please pause here and turn to page 11 of the INO and review this information regarding the dry running protection. An overload is detected when the current is excessive and the motor will shut down. The SQE electronics can detect overload conditions immediately and shut the pump down, preserving the life of the motor. Reaction times are much quicker and more accurate than traditional thermal relay protection devices. The fault is automatically reset after a 5-minute delay. Factory default settings for overload are defined in the chart on page 26 of the INO. Please pause here and take a moment to review all the information shown on that chart. Over/under voltage alarms. Fluctuation in voltage supplies, which are normal in some parts of the country, can cause excessive heating or loading of unprotected motors, resulting in reduced lifetimes. However, SQEs do not apply line voltage directly to the motor. Its built-in VFD circuitry acts as a buffer between line voltage and the motor, and by design can accept wide tolerances in input voltages and still provide stable, regulated power to the motor. However, if the voltage deviates outside allowable operating ranges, the alarm is declared. It will automatically reset itself when voltage returns to the allowable operating range. The trip points for these alarms can be found on page 26 of the I&O. Overtemperature is detected when the motor temperature exceeds critical levels and the pump is stopped. It resets itself automatically when the temperatures return to within allowable operating ranges. Again, trip points can be found on the chart, page 26 of the I&O. Now let's consider the second main component of the system, the CU301 control unit. First, remember this box is not a VFD. It's a controller designed to measure the pressure and then command the pump to start and stop or speed up and slow down. We'll talk about how it does this in just a few minutes. The user interface is extremely simple, consisting of only 3 buttons, the on-off button and 2 buttons for raising or lowering the desired pressure set point. Pressing the on button does not necessarily start the pump. It just enables it to start the pump if pressure conditions require it. However, pressing it to stop the pump will immediately turn it off. The on-off button can be used to reset alarms and can also be used to force the pump to run at maximum speed. As described on page 9, by pressing the on-off button and holding it for more than 5 seconds, the pump will run at the maximum speed for as long as the button is held. This can be useful in testing the operation of the system and the ability of the unit to perform. But be careful, forcing the pump to run at maximum speed can possibly produce an overpressurization, resulting in the opening of relief valves. Keep in mind that pressing the off button does not remove power from the SQE. The SQE is always energized whether the pump is running or not, so to service the pump, always disconnect power from the mains. The desired pressure set point is selected by simply pressing the up or down arrow. Additionally, these 2 buttons can be used to lock the front panel controls out of operation. This can be used as a safeguard to prevent an unauthorized person from changing the pressure set point. To do this, simultaneously press both the up and down arrows until the locked LED stops flashing. Do the same to unlock the controls. The serviceman LED will light if any alarms have been declared which stop the pump from operating. The homeowner can try to reset this alarm by pressing the on-off button twice. If alarms persist, it will be necessary to troubleshoot the system by observing the internal diagnostic LEDs or by use of the R100. This subject is covered extensively in the diagnostics module. The pump status LEDs indicate the status of the pump. When it's running, the green LEDs come on in a flashing pattern. If the SQE declares a dry run alarm, the LED shown in the circle will light. The dry run alarm automatically resets after 5 minutes and attempts to begin normal operation. However, if the well has not recovered, the alarm will recur and the cycle will repeat. Now let's talk about the third component of the SmartFlow system, the pressure sensor. It's important to understand a little bit about the pressure sensor and how it works, as it plays a critical role in providing information to the system from which most of the commands to the motor are based upon. The specifications shown on the screen are also printed on the sensor label, as well as wiring instructions. First, it's an electronic device which requires power to operate. It receives this power from the 24-volt DC terminal located in the CU301. It can measure water pressure between 0 and 120 psi and then sends that information back to the CU301 encoded in current flow between 4 and 20 milliamps, with 4 milliamps equal to 0 psi and 20 milliamps equal to 120 psi. Pressures between these 2 limits will generate current flow between 4 and 20 milliamps. Finally, note that the fitting is 1/2 inch NPT and designed to be screwed into a T using the lower hex flats. Don't screw the sensor into a T using the upper hex flats, or you run the risk of twisting the sensor in half and destroying it. The upper hex flats are for holding the sensor in place while attaching conduit to the upper part of the sensor if so desired. The sensor is not waterproof, so it must not be submerged underwater or buried in soil. If water can find its way into it, it'll be destroyed. In the diagnostics module, we'll go over different ways to troubleshoot the pressure sensor. fourth and final component of the SmartFlow system is the diaphragm tank. In SmartFlow constant pressure systems, the tank serves a different purpose than in traditional pump and tank systems. In those systems, the pressure tank is utilized for both storage and to provide adequate drawdown with the goal of minimizing pump runs. Why is this important to minimize pump runs? Recall our discussion regarding inrush currents to conventional motors on startup and the need to let the motor windings cool between starts. Since the motor is soft started, there's no need to minimize starts. Thus, the need for a large tank is eliminated. A minimum 2-gallon size is recommended. Larger tanks can be used, but a lower tank air pressure may be required to obtain ideal constant pressure regulation. The pressure tank acts primarily to provide enough water to meet initial flow and pressure demands until the pump ramps up to speed and takes over, typically in a matter of a couple of seconds. Before shutting off, the SQE will raise the pressure to 7 psi above the set point, thus preloading the tank with extra water in preparation for the next start cycle. Secondly, the tank serves as a buffer to minimize fluctuations during flow changes. The proper amount of pre-charge pressure in the tank is equal to 70% of the set point pressure. For example, if the desired set point is 60 psi, charge the tank to 42 psi. A conversion chart helping you with this is found on page 8 of the I&O. Now that we've covered the 4 components of the SmartFlow system, let's talk about how the system uses them to produce constant pressure. We mentioned that the CU301 controls the pump's operation, but exactly how does it do that? The only wires between the CU301 and the SQE are the 2 power leads. Grundfos uses an innovative approach to carry messages between the CU301 and the SQE by placing them on the power leads in the form of high-frequency data communication. It's a common technology used in security systems, baby monitors, and intercom systems which use existing AC power in a home to carry voice or data. Commands such as on, off, motor speed, and all diagnostic information move over these wires. It's a two-way street with control commands flowing from the CU301 and performance and diagnostic data flowing from the SQE. Information such as motor speed, temperature, and power consumption, as well as any alarm conditions encountered, is sent up from the SQE. This data can then be viewed by use of the Grundfos handheld service tool, the R100. A full discussion of the powerful capabilities of the R100 will be discussed in the diagnostics module. When messages are sent between the units, they are addressed by a preset number. For example, CU301 number 1 sends messages addressed to SQE number 1. Both units must agree on this number before they can communicate. From the factory, both are set at number 1 and nothing needs to be done to establish proper communication. However, if multiple units are installed at one site, it's necessary to change this message address number in order to ensure correct communication between each pair of CU301 and its SQE. Some customers will install multiple units in one well in order to obtain double capacity for periods of high flow demand. In these situations, certain precautions must be followed. These precautions are fully explained in the last paragraph of section 1.2 on page 5 of the I&O. Further instructions can be found in section 5.3.9 on page 19. It's a good idea to pause this program here and review these sections in the I&O. If the CU301 pump power cables are run parallel in wiring trays or conduit and less than 10 to 12 inches apart, the possibility for undesired communication between units exists. When this occurs, intermittent or continuous no-contact alarms are typically seen. Other unexpected errors may also be seen. It's important to read the I&O for instructions related to installing multiple units at one site. How does the pump know when to stop? Since there's no traditional pressure switch telling the pump when to turn on and off, an alternate means must be used to tell the pump when flow is ended. In order to stop the pump when no water is consumed, the CU301 performs a flow detection test every 10 seconds. The graph on the screen can be found on page 6 of the I&O. This graph illustrates how that test is accomplished. The vertical axis represents pressure and the horizontal one time. Every 10 seconds the pump speed is reduced slightly, and if a pressure drop is seen, it's assumed that water is being used and the pump will resume its normal speed and then repeat the test 10 seconds later. If no pressure drop is measured, it assumes that no water is being consumed and the pump will ramp the pressure to 7 psi above set point and stop. Don't confuse the frequency of this test with the rate at which the CE301 reads pressure from the sensor. This flow test is conducted once every 10 seconds, but the CE301 is actually reading the pressure many times per second. Referring to the photograph on the screen, note the position of the safety relay. This is a normally closed relay through which all power to the pump flows. If for any reason the electronics fail, the relay will open, stopping the pump and preventing it from operating uncontrolled. Additionally, if the power line communication between the SQE and the CE301 is lost, the CE301 will begin operating the relay as a pressure switch, cutting in at 7 psi below set point and cutting out at 7 psi above set point. This fail-safe feature is designed to provide the customer with water even though system failures may have occurred until a serviceman can investigate. The CE301 has to be reset using the on-off button after each 250 start-stop cycles. The serviceman LED on the front panel will also be lit. A pump status relay has been added to units produced after April of 2006. This dry contact relay, accessed by terminals 8 and 9, closes when the pump runs and opens when the pump stops. It can be used to drive external devices that need to operate in sync with pump operation. This concludes the System Components module. We hope that it's been instructive and worthwhile and encourage you to view the other 2 modules in this set of instructional videos. We thank you for your attention and we appreciate your business.